So, what if we could build computers that are as ridiculously efficient as the human brain? Today, we're going to dive into a pretty revolutionary approach to computing that does just that, by taking its cues from the most powerful processor on the planet. You know, this quote right here, it really highlights a shocking truth. A researcher named Jason Eshrajian was told as a kid that saying thank you is free. But, well, as OpenAI CEO Sam Altman pointed out, that's not exactly true anymore. The AI we use for even the simplest things, like just generating a polite phrase, it burns through an absolutely astonishing amount of energy. And the scale of this energy gap is, well, it's staggering. Training a model like GPT-4, you're looking at around 2.5 megawatts. That's enough power for a whole small town. Your brain, on the other hand, it does every single complex thing you can imagine on just 20 watts. Seriously, that is less power than a dim light bulb.
This incredible difference in efficiency, it's not just some fun fact. It's genuinely one of the biggest challenges facing the future of tech and AI. So the big question is, how in the world do we bridge that gap?
Well, it turns out the answer might lie in a field called neuromorphic computing. And the whole idea is to learn from the brain's most brilliant design principles.
This was pioneered by a Caltech professor, Carver Mead, and it's all built on a really simple observation. Biological solutions are often just way more effective than our engineered ones. So, why not let evolution's greatest hits guide our technology?
But, and this is important, the key word here is inspiration, not imitation, right? We don't build airplanes with flapping wings because a plane has to carry hundreds of people, something a bird never has to worry about. And by the same token, our brains can't focus on millions of queries at once like an AI can. So it's all about taking the right lessons for the right problems.
So what are the most important principles we can actually borrow from the brain? Well, it really boils down to three core concepts, what we'll call the three S's. So these three ideas, spikes, sparsity, and static suppression, they are the fundamental blueprint for building these brain-inspired, super-efficient computing systems. Let's break them down. First up, spikes. See, unlike a traditional AI, which uses all these complex numbers, our brain cells communicate with really simple electrical pulses. It's either on, which is a spike, or off, which is silence. It's basically biology's version of ones and zeros. And the power of that simplicity is just immense. In computing, the most expensive thing you can do is move data around. So if a neuron is silent, if it sends a zero, the system doesn't have to go access thousands of parameters connected to it. You just skip the entire calculation, and that saves a ridiculous amount of energy. And that leads us right into our second S, sparsity. Because of those spikes, the vast majority of your neurons are actually silent at any given moment. This means the data flowing through your brain is incredibly sparse. It's mostly just zeros, with only a few ones lighting up. And finally, we have static suppression. Our senses are what you'd call event-driven. Your eyes and your brain don't waste energy constantly reprocessing the wall you're staring at. No, instead, they focus only on what's new or what's changing, like, say, a person walking into the room. A perfect way to see this in action is with something called an event camera. Look here. The conventional camera on the left, it's capturing everything, wasting all this power on the background that isn't changing. But the neuromorphic camera on the right, it only records pixels where the brightness changes. It sees the cars moving, it even sees the tiny raindrops, all while using just a fraction of the power. It's brilliant.
So, okay, if these principles are so powerful, why aren't all computers neuromorphic by now? Well, the early models, they ran into a pretty major problem: scale.
So here's the bottom line. While these early brain-inspired models were super cheap to run, they just couldn't match the raw performance of the giants, like ChatGPT. See, as you give traditional AIs more and more data, their memory needs just explode, and the early neuromorphic networks, they just couldn't keep up.
The big breakthrough came from rethinking the very mathematical heart of modern AI. I'm talking about matrix multiplication, which is incredibly powerful, but also incredibly costly.
So researchers came up with this matrix multiply free model, and it has two really clever tricks. First, it simplifies all the math, using only three values: -1, 0, or +1. That alone slashes memory needs. And second, it gives the model a finite memory, and just like our brains, it teaches it to forget old information to make room for what's important now. And when this new model was tested on real-world neuromorphic hardware, things like Intel's Low-Hi 2 chip, well, the results were an absolute game changer.
Okay, let's just look at the data. This chart shows throughput per watt. It's basically how much work you get done for a given amount of energy. Now see that model on the left? That's your standard AI. Now look at the neuromorphic model on the right. It's processing a vastly larger amount of information for the exact same power. Higher is better here, and as you can see, it is not even close.
Now let's flip it around. This chart shows the energy cost to generate a single word, or a token. And here, obviously, lower is better. Again, the standard model is that tall bar. The neuromorphic model is so much more efficient. It barely even registers on the chart. It's just a whole different league.
And this is the incredible result. We can now run a massive billion-parameter language model at a human-readable speed using just 13 watts. Think about that. That's less power than the 20-watt human brain that it was inspired by. We have officially beaten our biological benchmark. This incredible leap in efficiency, it's not just an improvement, it's a fundamental shift. This paves the way for AI that's sustainable, that's accessible, AI that can run on tiny devices, not just in massive data centers. So if a simple thank you costs millions today, what happens when it costs almost nothing? Once we free AI from its energy constraints, what will it truly become capable of?